In this video, we will be talking about the topic of correlation and regression analysis. Our learning objectives are to draw and analyze scatter plots for two data sets, how to calculate the correlation coefficients, how to determine if the correlation coefficient is significant, how to find a regression line for two data sets, and then how to use the regression lines to make predictions. Before we get started, I just want to make a comment that many of the calculations in this section are pretty time-consuming and a little tedious to do completely by hand. For that reason, understanding how to use technology to help with this material is really important for this section. There's two supplementary videos in Brightspace that go over how to use a TI-30 calculator to do many of the calculations we'll go over here. And there will be an additional video posted of me going over how to use Excel. We'll use Excel to specifically kind of go over the some of the examples that we do in this video. So I just would encourage you to go look at those videos in addition to this one, and that will help you greatly with the homework as well. With that in mind, let's go ahead and get started. When we gather comparative data in order to determine if there are any meaningful connections, we can begin by plotting a graph, designating one set of data as the X variable, also referred to as the independent variable. Okay. And the other as the Y variable, also referred to as the dependent variable. This graph is called a scatter plot. A scatter plot is a graph of the ordered pairs X and Y consisting of data from two data sets. After a scatter plot is drawn, we can analyze the graph to see if there is a noticeable pattern. If there is, like the points falling in an approximately straight line, we can conclude that the two variables might be related somehow. If there appears to be a reasonably clear relationship between the variables, we might study that relationship further by trying to find an equation that relates the variables. This is known as regression analysis, in which we will learn about later in this section. Let's begin with an example. We want to draw and analyze a scatter plot. Let's say that a medical researcher selects a sample of small hospitals in the state and hopes to discover if there is a relationship between the number of beds and the number of personnel employed by the hospital. So we want to answer two questions. A, do you think there should be a relationship between these two data sets? And maybe describe any relationship that you might expect. And then B, draw a scatter plot for the data shown. Does it look like there is a relationship between the data sets? Okay. So again, what we're trying to explore is if there is a relationship between the number of beds and the number of personnel employed by the hospital. Okay, so what would we expect here? Well, as a general rule, you would think that larger hospitals would have more beds in them, right? That makes sense. You would also think that larger hospitals would employ more personnel. So it seems reasonable to predict that less beds then would go along with less personnel, and more beds would go along with more personnel, right, as a general rule, right? So that's what we expect. Okay, we might say expected relationship say less beds would go along with less personnel. And conversely, we would expect that maybe more beds would go along with more personnel. Right? That would make sense. Okay, so now we'll sketch a scatter plot. So we have actual data here, right? This is data taken from a sample of small hospitals. Right? It looks like we have data from, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hospitals. And for each hospital, 2 pieces of information was collected: the number of beds in the hospital and the number of personnel employed by the hospital. We are choosing to make number of beds the X variable and personnel the Y variable. To create a scatter plot, first we need to draw and label the axes. The information in the table, right? So like we said, X is number of beds. We always put X along the horizontal axis. We call that the X axis. So we'll go ahead and sketch my axes here. This is X, this is Y. My X axis is, we'll just label it number of beds. Okay. And then my Y, I will label this as personnel. Like so. Okay. Then I got to scale my axes. If you look at the actual data here, it looks like my numbers in the X category, it looks like the smallest number here is probably 28. The largest number here looks like is 95. So perhaps when I'm scaling my data, I'm going to start at 0 and go in increments of 10. 10, 20, 30, 40, 50, 60, 70, 80. Looks like I'll have to make this a little bit longer. So let's do that. 90, 100. Okay. As far as Y is personnel, and it looks like our numbers here range from a low of 72 to a high of 366. Okay, so pretty wide range there. I think what I'll do is go in increments of 50. So 0 again is at the bottom. So let's say that's 50, 100, 150, 200, 250, 300, 350, 400. I mean, that's really enough. In fact, you know what? Sorry, didn't mean to. This is why I will, in the separate video that will be posted, I'll go over how to do these scatter plots using Microsoft Excel, which is really kind of a better way to do it. But doing it by hand can be a little trickier. What I want to do is spread these out a little bit more, just to make the graph a little bit better. Okay. Okay. There we go. Let's move my Y and put it up there. Okay. There's my setup. Okay, so now that I have my axes set up, what I need to do is actually graph the data. So what I'm going to do is treat each X and Y value as an ordered pair, right? So my first ordered pair, there's an X value of 28 and a Y value of 72, right? So I would find 28 on the x-axis, which is, I'm just going to have to approximate, it's a little bit less than 30. 56 on the y-axis, a bit more than 50. Figure out where that x and y value kind of meet up on the graph, right about here. So let's plot a point there. Okay, so right about there. And then we keep doing that. There should be 10 points on the graph corresponding to each pair of data, right? Then I have x equals 56, y equals 195. 56, 195, I will estimate that about there. Then I have x equals 34 and y equals 74, okay? 34, 74, let's estimate that to be about there. Then I have x equals 42, y equals 211. X equals 42, y equals 211. Again, looks like right about there. Then I have x equals 45 and y equals 145. So 45, 145, I'm going to say right about there. Then I have x equals 78 and y equals 139. So x equals 78, y equals 139. I'm going to estimate that to be about there. Then I have x equals 84 and y equals 184. X equals 84, 184, right about there perhaps. Then I have x equals 36 and y equals 131. X equals 36, y equals 141, about there. 131, sorry. Is that right? Yeah, okay. Then I have x equals 74 and y equals 233. 233, about there perhaps. And then x equals 95 and y equals 366. Okay, so 95, 366 is up about here. Okay, so there's my scatter plot. It's not perfect because I did this completely by hand, right? But it gives you a pretty good idea of what a scatter plot for this data would look like. And if you look at the scatter plot, what you observe is there's generally an upward trend to the data, right? I could sketch a straight line on top of my scatter plot, and the straight line, while it would not fit the data perfectly, it wouldn't be a terrible fit either, right? You can see a pretty obvious upward trend, which does seem to indicate that as number of beds gets bigger, that generally correlates with larger personnel numbers as well, right? So it does pretty much confirm our prediction. Lower numbers of beds tends to go with lower numbers of personnel, and higher numbers of beds tends to go with higher numbers of personnel. The scatter plot supports what we would expect to see. Now, there are several types of relationships that can exist between the x values and the y values in a scatter plot. These relationships can be identified by looking at the pattern of the points on the graphs. The types of patterns and corresponding relationships kind of fall into about four kind of different categories here. A positive linear relationship exists when the points fall approximately in an ascending straight line from left to right, where the x and y values increase at the same time. See figure 11.26a, this one right here represents a positive linear relationship. Even the scatter plot that we just created up here is a pretty good representation of a positive linear relationship. Okay. 2, a negative linear relationship exists when the points fall approximately in a descending straight line from left to right. That would be like this one, figure 11.26b. In this case, as the x values are increasing, the y values are decreasing. 3, we could have a non-linear relationship where the points fall perhaps like a curved line. This would be like 1126C. The relationship is described by the nature of the curve. And then we could have something like 1126D here, where really no relationship exists, where we just kind of see a randomized bunch of dots, but there's no discernible pattern to the points, like 1126D here. So yeah, the relationship between the variables in the example we just worked out with the hospital beds versus personnel might be described as a positive linear relationship. It looks like as the number of beds increases, the number of personnel also increases. Okay, deciding whether or not two data sets are related by simply looking at a scatter plot is a pretty subjective process. So it would be nice to have a way to quantify how strongly connected data sets are. This is the purpose of our next topic, which is the correlation coefficient. The correlation coefficient is a number that describes how close to a linear relationship there is between two data sets. Correlation coefficients range from -1, which represents a perfect negative linear relationship, to +1, which represents a perfect positive linear relationship. The closer this number is to 1 in absolute value, the more likely it is that the data sets are linearly related. Linear is really just a word that means straight line. Okay, so a linear relationship is a relationship that can be described by a straight line. A correlation coefficient close to 0 indicates that the data sets are most likely not linearly related. This could mean that they are related in some nonlinear way, or they're not related at all. Okay. So this diagram here kind of illustrates the spectrum. -1 is a perfect negative linear relationship. On your scatter plot, that would be represented by dots perfectly lined up in a straight line with a downward slope. +1, this would be a perfect positive linear relationship. On your scatter plot, that would be represented by dots perfectly lined up in a straight line with an upward slope. And then 0 is no linear relationship. Most often, correlation coefficients fall somewhere between 0 and 1, or somewhere between 0 and -1. In the real world, you pretty much never see perfect relationships. So you don't see coefficients of exactly 1 or -1, but you can see coefficients that are pretty close to 1 or -1, which would be fairly strong linear relationships. Okay. It's customary to use the letter r, a lowercase r, to represent the correlation coefficient. It doesn't depend on the units for the two data sets. It's just a number. It doesn't have any units associated with it. And it also doesn't depend on which set you choose for the x variable. Okay. So let's look at a couple of examples. Example 2, we want to estimate correlation coefficients. And then we'll look at an example where we actually calculate a correlation coefficient. Okay. Example 2. Based on our description of the correlation coefficients for two data sets, make an estimate of the correlation coefficient for each scatter plot in figure 1126. Okay. So let's just go look at the scatter plots, and we will just kind of write down our estimate right next to each scatter plot up here. Okay, so here's our 4 scatter plots. The first plot right here shows a positive linear relationship. It's pretty obvious. Now, the points are not perfectly lined up in a straight line, but they're close enough that you see an obvious trend. Okay, so the R value should be close to 1. So we say R is close to 1. It won't be equal to 1. It's not a perfect relationship, but it's a strong relationship because the trend is obvious. B shows pretty much the same idea, except the slope is in a downward direction instead of an upward direction. So for this one, R is close to -1. Okay. The third and fourth plots here don't show linear relationships. The correlation coefficient can only be used to describe a linear or a straight line relationship. It's true that we do see a relationship in this in the diagram for part C here, but it's not linear. It's not a straight line. And then for D, we don't see really any relationship at all. So for both C and D, we would expect the R value to be close to 0. Okay, R is close to 0 for both of these. And that's because neither of these diagrams show a linear relationship, and the value R is used only to describe a linear relationship. Okay. Let's come back down here. So we've done example 2. Now let's talk about actually calculating the correlation coefficient. In order to find the value of the correlation coefficient, we use the following formula here. This is a kind of a big, ugly looking formula. Remember that this symbol right here, this is the Greek letter sigma, which represents a sum. So we're calculating a bunch of sums and plugging those sums into this formula and then simplifying. So down here, we kind of just have a description of what everything in the formula represents. N equals the number of data pairs. In the example, in the scatter plot we created for the first example, we had 10 pairs of data, so N would be 10. This is sigma x. It represents the sum of the x values. This is sigma y. It represents the sum of the y values. This is sigma xy. It represents the sum of the products of the x and y values for each pair. This is sigma x squared. This represents the sum of the squares of the x values. And then sigma y squared, which represents the sum of the squares of the y values. Obviously, this is a pretty complicated formula. So to work this out by hand, it's a little tedious, but it helps to arrange the information in an orderly table. In fact, that's pretty much essential. So in example 3, what we're going to do is find the correlation coefficient for the data in example 1, the hospital bed numbers along with the number of personnel for those 10 hospitals. Okay. So here's the worked out solution. So step 1, we need to make a table as shown with the following headings: x, y, xy, x squared, and y squared. Step 2, find the values for the product xy, the values for x squared, the values for y squared, and place them in the columns as shown. Then find the sums of the columns, right? So here's my columns. I have 5 columns. My x and my y columns, these are just my raw data. So x here represents the number of beds, right? And y represents the number of personnel for each hospital. So this is just my raw data. In the column labeled xy, the numbers in this column are found by taking each value of x and multiplying it by the corresponding value of y. So like 2016, that would be 28 times 72. 10,920, that would be 56 times 195, and so on. In the x squared column, you square all of the numbers in the x column. 784, that would be 28 squared, which means multiply it by itself, right? 28 times 28 is 784. 3,136, that is 56 squared, and so on. Then we do the same thing for the y values, right? 5,184, that is 72 squared. 38,025, that's 195 squared, and so on. So once you find all the values for each column, then we sum them up, right? So these are my sums at the bottom, and these are just the sum. You add up the numbers in each column. There should be 10 numbers in each column, and you add them up. These numbers at the very bottom are the sums. Once we find all the sums, we substitute them into the formula. This is step 3. Substitute them into the formula and evaluate. Note that there are 10 data pairs, so my value of n is 10, right? So here's what that looks like down here. Here's my formula. I replace n with 10. Sigma xy gets replaced with this number, 113,865, right? Sigma x gets replaced with 572. Sigma y gets replaced with 1,750, and so on. And then you really just need to kind of carefully work this out. You'll need a calculator. Break it up into several steps. So like what we did here is simplify the numerator. The numerator simplifies down to 137,650, and simplified the two numbers underneath the square root, which are these two numbers. Once you get it down to here, it'd be pretty easy just to do that final step in your calculator, and you end up with about 0.748. That's our correlation coefficient. Okay. And it's fairly close to 1, right? It appears to confirm what our eyes tell us about the scatter plot in example 1. It's certainly not a perfect linear relationship. It's not equal to 1, but it does tend to indicate that as bed space goes up, the number of personnel does as well. Okay. I'm just going to pause here. As you probably noticed, this calculation is pretty lengthy, pretty time-consuming, but at the same time, this is a very useful number to have. In the real world, this number is almost never done, this calculation is almost never done by hand. Technology tools are used to do this for us, whether it's a scientific calculator or a program like Microsoft Excel, right? So in the homework, you are not expected to do these calculations by hand. I think it's helpful to see it worked out for one example so you know where this number comes from. It's not just kind of made up out of thin air, but you are encouraged to make use of your technology tools on the homework, and I encourage you to watch those other videos to learn how to do that. Okay, word of caution. Based on what we have seen in examples 1 and 3, we might ask the question, does having more beds cause a hospital to have more staff? Or does having more staff cause it to have more beds? All right, the answer here is neither. All we know so far is that the two variables appear to be related in a linear way. But this says exactly nothing about whether one is caused by the other. Correlation, we observe a correlation. That does not mean there's a causation relationship. Okay, correlation does not mean causation. Sometimes there is a causation, sometimes there's not, right? But just because we can see a strong relationship exists does not mean we can conclude that changing one variable causes the other one to change. Okay, so that's just a word of caution. Okay, so next we will tackle the issue of how to interpret the correlation coefficient. Statisticians have traditionally agreed that when we conclude that two data sets have a relationship, we can be satisfied with that conclusion if there is either a 95% or 99% chance that we're correct. This corresponds to a 5% or 1% chance of being wrong. These percentages are called significance levels. let's explore this a bit more. Here we have a table, and this table shows what are called significant values for the correlation coefficient. Right? So we have a sample size column, and then we have significant values for a 5% and a 1% level of significance. We know that the more data we have, the more likely those data are representative of the population. Not surprisingly, the value of R needed to be reasonably sure that two data sets are correlated is higher for small sample sizes and lower for large sample sizes. In Table 11.4, we see that the minimum R values needed to have a 5% and 1% chance of being wrong when we conclude that two data sets are related. Okay? So like basically, if you have a sample size of 10, like in our example, and we want only a 5% chance of being wrong, then you would need to have a correlation coefficient of at least 0.632. Okay. If you want an even a higher level of precision, maybe only 1% of being wrong about there being a correlation, we'd need a correlation coefficient of at least 0.765, and so on. Okay. So that's how this table works. If it says the absolute value of R, that basically means for the purpose of this table, we don't really care whether it's a positive or negative correlation. All we care about is, whether there is a linear relationship or not, right? So we can, if it's a negative relationship, we can just kind of ignore the negative sign, because all we're caring about is the strength of the relationship, not whether it's positive or negative, right? So if the absolute value of R is greater than or equal to the value given in Table 11.4 for either the 5% or 1% significance level, then we can reasonably conclude that the two data sets are linearly related. Okay, example 4. Determine if the correlation coefficient R equals 0.748, found in example 3, is significant at the 5% level. Okay, so we have the value of R. We also need to know the value of N. N is my sample size. It's also the number of data pairs. The data we collected was based off of a sample of 10 hospitals. So that's my value of N. So if I go up here, like I did earlier, right, you find N equals 10, and you find your 5% level, and we have 0.632. In this case, my value of R, 0.748, is greater than that value from the table, 0.632. Okay. So based off of this, we can say that there is at least a 95% chance that the data are significantly related. Okay, at least a 95% chance that they're significantly related. Okay. However, we cannot conclude that there is a relationship between the data sets at the 1% significance level, because notice that if we go to N equals 10, here's the 1% significance level. You would need to have a correlation coefficient of at least 0.765 to conclude a definite relationship at the 1% level. Our correlation coefficient is a little bit smaller than that, right? 0.748 is less than 0.765, right? So we can be 95% sure that the data sets are linearly related, but we cannot be 99% sure, right? How should we choose whether to use the 5% or 1% significance level in a given situation? It really depends on the seriousness of the situation and the importance of drawing a correct conclusion. That's kind of where it comes down here. But there's some amount of subjectivity in that. Okay, moving on to our next topic. Once we have concluded that there is a significant linear relationship between two variables, the next step is to find the equation of what we call the regression line. Through the data points. If you look back at the scatter plot in example 1, let's just go back there real quick. Here's the scatter plot we made back in example 1, right? Kind of take note of that. Okay. You can see a general trend among the points from lower left to upper right. You could probably put a straight edge down and draw what seems like the closest approximation to a line by kind of splitting the difference between the points that don't line up exactly. That is what a regression line does, but instead of guessing, we are finding the single line with a special property. The overall distance from each point to the line is a minimum. For that reason, the regression line is also called the line of best fit. Recall from algebra that the equation of a line in slope-intercept form is of the form y equals mx plus b, where m is the slope and b is the intercept, is the y-intercept. In statistics, the equation of the regression line is written as y equals a plus bx, right? So it's just a different standard as far as how notation works, where a is the y-intercept and b is the slope. This is the equation that will be used here. In order to find the values for a and b by hand, we need two formulas. It's more common to use technology, and like I said, there will be a separate video posted that goes over how to do this using Excel. There's also some videos posted on how to do this with the TI-30 calculator. But here's the formulas for doing these calculations by hand. Right, so again, this is the formula for finding the value b, which is the slope. And here's the formula for finding the value a, which is the y-intercept. If you've already done all the work to calculate the correlation coefficient, then doing the additional work to find the regression line is not a ton of extra work because you've really already calculated all of these sums already, right? So you've done kind of the hard work already if you've found the correlation coefficient. Okay. So we already, so in example 5, it says find the equation of the regression line for the data in example 1. We already calculated the values needed for each formula when we found the correlation coefficient in example 3. So we just substitute into the first formula to find the value for the slope b. Right? Again, these numbers were calculated from the table in example 3 where we did the correlation coefficient. We just plug those numbers in, simplify down, round to about 3 decimal places is generally good enough. So my value of b here, my slope is about 2.708. Then I substitute into the second formula to find the value for the y-intercept, which is a. So for this one, you need sigma x and sigma y from the table from example 3. And then b is what we just calculated right here. That's the 2.708 value, and we divide by n, which is 10. That works out to be about 20.102. So the equation of the regression line then is y equals 20.102 plus 2.708 times x. Okay. After we find the equation of a regression line, we can see how it compares to the original data by graphing the line on the scatter plot. For the scatter plot in example 1, we can graph the regression line by plotting 2 points using the equation we found in example 5 that we just calculated. So choosing two x values between 0 and 100 so that the points will appear on the scatter plot. So, we just kind of arbitrarily chose x equals 30, plugged that into the equation and solved for y, which gave us approximately 101. And then x equals 70, plugged that into the equation and solved for y to get approximately 210. So the points 30, 101 and 70, 210 are on the graph. We plot those 2 points and then draw a line through them. So in figure 1128 right here, we have our scatter plot, which are the little red dots, and then we have my regression line plotted on top of the scatter plot right here. Okay, and the red line is the straight line that passes through these 2 points, 30, 101 and 70, 210. Okay. And you can get a pretty clear sense about how that regression line actually fits the data quite well. And in fact, it is the straight line that fits the data better than any other straight line. Okay, let's talk a little bit about the relationship between the correlation coefficient and the regression line. 2 things should be noted about the relationship between the value of r and the regression line. First, the value of r and the value of the slope b always have the same sign. If the slope is negative, r will be negative. If the slope is positive, r will be positive. Second, the closer the value of r is to +1 or -1, the better the points will fit the line. In other words, the stronger the relationship, the better the fit. Figure 1129 shows the relationship between the correlation coefficient and the regression line, right? So you can, in all of these cases, you can see the regression line plotted, but the top 3 scatter plots show a positive linear relationship. The bottom 3 show a negative linear relationship. And as you go from left to right, the strength of the relationship gets successively better. And what you see is that for a stronger relationship, the points tend to cluster closer to the line, whereas this one represents the strongest possible, right, where the points are perfectly lined up in a straight line. Okay, so this is for a correlation coefficient of 0.5, 0.9, and 1. And then we have negative 0.5 and negative 0.9 and negative 1. Now, one of the most useful aspects of finding a regression line is that it can be used to make predictions for one of the variables given a value for the other. Now, this is illustrated in our next example. Use the equation of the regression line found in example 5 to predict the approximate number of personnel for a hospital with 65 beds. So my equation was y equals 20.120 plus 2.7077 times x. So x here represents the number of hospital beds. So what I do is I take my equation and I just replace the x with 65 and I solve for y. And it makes sense to just round this to the nearest whole number. If I round to the nearest whole number, it's 196. So we would predict that a hospital with 65 beds will have about 196 personnel. Okay. Now, this does not mean that every hospital with 65 beds will have exactly 196 personnel, right? It's not necessarily saying that, but it's an estimate, right? It's a prediction that it would be probably somewhere in the ballpark, pretty close to 196 personnel. The stronger the correlation between the data values, the better these predictions will be. Caution, never use a regression line to predict anything unless you've already checked that the correlation is significant. If the correlation is not significant, the regression line is meaningless. It will not give you an accurate prediction. Okay, let's wrap up by just talking a little bit about correlation versus causation, which we alluded to a little bit earlier in this video. Here's a key phrase to remember when studying correlation and regression analysis. Correlation is not the same thing as causation. Knowing that two variables are related doesn't say anything about whether or not one causes change in the other. Here are some possible interpretations when two variables are significantly correlated. So we've got possible relationships between data sets. One possibility is that there is a direct cause and effect relationship between the two variables. That would be X causes Y. For example, water causes plants to grow, poison causes death, heat causes ice to melt, right? Sometimes there actually is a cause and effect relationship. 2, there could be a reverse cause and effect relationship between the variables. So this would be like Y causes X. Suppose that we find a correlation between excessive coffee consumption and nervousness. It would be tempting to conclude that drinking too much coffee causes nervousness. But it might actually be the case that nervous people drink a lot of coffee because they think it calms their nerves, right? So that's another possibility. 3, the relationship between the variables may be caused by a third variable. You could probably find a positive correlation between the amount of ice cream consumed per week and the number of drowning deaths for each week of the year. But this doesn't mean that eating ice cream causes you to drown. Both eating ice cream and swimming are more common during the summer months, and it stands to reason that more people will drown when more people are swimming. In this case, a third variable, which we could call seasonal weather, is affecting each of the original two variables. 4, there may be a variety of complicated interrelationships among many variables. For example, a researcher may find a significant relationship between students' high school grades and college grades, but there probably are many other variables involved, such as academic ability, hours of study, influence of parents, motivation, age, and instructors, right? 5, the relationship might simply be coincidental. For example, historians have noticed that there is a very strong correlation between the party that wins a presidential election and the result of the Washington NFL team's final game before the election. However, but good old common sense tells us that this relationship has to be a coincidence, right? So it's just a pure coincidence. There's really nothing going on there. So all that to say, right, just because we can establish that a relationship exists between two variables, we have to be a little bit cautious in interpreting the reasoning behind that. Sometimes the reason for the relationship is a little bit harder to see, and we definitely cannot just immediately conclude that there is a cause and effect relationship. There might be, but many times there's a different but still valid reason for the existence of the relationship. That wraps up this video, so we'll stop here for now. And again, please view the other videos on Brightspace that go over how to use technology, and thank you for watching.